I'm going to briefly recap Markov decision processes and also kind of give one more example, and then close and probably defer some discussion maybe to the last lecture if I get time. So recap that formally a Markov decision process had this interesting Markov property where the probability of transitioning to a new state from a current state given some action is as good as the probability of transitioning to a state given the entire history after having taken an action. Okay, and I'll give one more example to motivate this, but let's say we have this maze. And this, let's say this is the start state, certain cells are shaded out, and this is the goal state, okay, and we want to find a path from the start state to the goal state. There may exist more than one path, but there are certain tempting paths or say tempting next steps which might not lead to the goal at all, right? That's a characteristic of the maze. So let's look at this kind of assumption. What we are saying here is the probability of transitioning. See, if I were here for example, I would have got completely blocked. So probability of transitioning to this state given my action could be that I move to the left, right, top, above or below, top or bottom, whatever, right. So I might try and take some action here. So the probability of transitioning to a state, now what is the state? The agent state is its knowledge of the maze, right. So the Markov decision process assumption is that my agent's knowledge of the maze is the new knowledge of the maze, the new state I will be in, given the previous state and the action I took, movement to say the left, is as good as the knowledge, the probability of transitioning to this new state, new knowledge state, given the action of moving left from the entire previous trace, all the steps I have taken so far. Okay. So this is the Markov assumption. Now you may debate whether this is not completely correct, but you must know that in a maze, because I don't really, I mean somebody may say find a shortest path, but I really don't know the structure of the maze, right. So this is not completely unrealistic either. So when in fact there are also other issues, I mean two situations may be indistinguishable from each other. I may not even know how to distinguish one situation, say this one, from another situation where we have a similar say block. So think of these two situations. I might move here and let's say I get to this, oh there's no path here, but let's say there was a path here. So these two situations look very indistinguishable from each other. Okay, so just talking about the strengths and weaknesses of such a Markov assumption. So history is basically for the entire history, the current state is a sufficient statistic. You've done sufficient statistics in your 215. The mean, for example, in the case of a Gaussian, could serve as a sufficient statistic. In any case, mean and the variance. So here's the maze example, but now let's try and understand what all the jargon we have developed, how does it map here. So we talked of the following. So we talked of actions, we talked of states. Now states, as I said, you could think of the knowledge state, my knowledge of the maze, the agent's knowledge of the maze, all the possible states to be enumerating that knowledge in a discretized manner. There are also rewards. So the more time I take to get to my goal, the more I should be penalized. So the model being used here is that there is a -1 per time step reward, or -1 is basic penalty of 1 or a reward of -1. Okay, so whether I move this way or this way, I incur a reward of -1, and I incur that reward after I make the move. Okay, the actions are north, east, south, west, so that makes more sense than referring to them as left, right, etc. So north, east, south, west. That way we are in the same frame of reference as the agent. And here the state that we are talking about is the agent's location. This is one way of codifying the knowledge, where exactly in the maze I am located. What are policies? So policy would be a mapping from a state to an action. It can be deterministic or probabilistic. So let us say this is exactly the policy, a deterministic policy for every state. I could just enumerate the policy for almost every node here. I could just do this. This is what I decide to take. Now we want to discover the best policy, right? But this is just one policy. So this is a deterministic policy. So the arrows represent one such deterministic policy for each state S. So now question would be, what would happen if you had a stochastic policy? Stochastic policy would be a mapping but probabilistic, right? So example would be pi of north given a particular state S1 is 0.5, I might be more likely to go north than say east, west or south, where I might just divide 0.5 by 3 and budget that for the remaining. So this would be an example of a probabilistic policy. It's an example. And now there is some transition probability. So there is a policy which tells the action I took, but what is the probability of transitioning to a state? Now what is a state? State is my understanding of where I am in the maze, right? The agent's location. Here the pi should sum to 1 across all possible actions I can take from a current state. Now it will depend on how you are structuring the problem. The question is, what if you go to the north and there is a wall you hit, there is this black patch there, right? You can do two things. What we can do here is that if you hit a wall, if you can't just take that action, that doesn't exist. You can't, there's no possibility of moving across a wall. But then there's another formulation, hopefully you may see that in your safe quiz today. But the another formulation is that you hit the wall and you incur some reward. So both are possibilities. So I'm not getting into the details of any specific policy, just giving examples. Okay, so now this is where we talk of the model. What is a model? Generally when model is being referred to, we are referring to two things, the reward and the probability of transitioning. So remember, when we look at expectation, we always had these two multiplied together, right? Reward into the probability of both are arguments of the same, that they have similar three arguments, S prime, S and A. Probability of transitioning to S prime given I took an action A and my previous state was S, right? My probability of being in a particular location after I went north given that I was in some other location, that's the semantics, and the reward associated with this transition. So these two are often referred to as the model. And this is related to learning. So if you what do you learn here? So one thing that you could consider learning is this transition probability and what will be the right reward. Okay, so you would learn this from multiple such mazes. So you would be left in one maze, you learn something from there, go to another maze. So you want to borrow these learnings on the model. And as you can see, just to contrast this picture with the previous one. The previous one, you had a lot more white spaces here, right? Whereas here, you are looking at the partial transition model. I mean, whatever my understanding of the model so far is, in terms of where I am located. Okay, so this is one possible representation, one possible probabilistic values, set of values associated with the model, and the reward. Now rewards, we have kept it very plain here. We just said -1, right? Because the more time I take to reach my goal, the unhappier I am. Agent wants to reach the goal really fast. So this is -1. Here we have disallowed jumping or penetrating a blacked out cell. You could also associate a reward with that if you want, but we have not done that. And the reward is the same for all actions and all states, as long as you don't bang into a wall. Based on this, now you can compute your value function. What is the value function? Value function is the cumulative reward. So it will be parameterized by a particular policy. The policy that I took, the policy that I showed using arrows in the previous slide here. So consider the product of the probability of transitioning and reward under a particular policy. So this would give me the average expected cumulative reward. And this is starting at a particular state, let's say S, and the S could be just the starting state. This is what? As I said, this is the expected reward, cumulative reward. Consider the step the reward I would get. So let's say this is ST, a particular state. I get the reward at t+1 when I make a transition from ST to some other state, plus RT+2 and so on. You could also start discounting your history. The more you have moved away from the goal, the more you are going to learn, or whatever you are going to plan based on the last move or the last few moves. So you could add this gamma square and so on. Okay. So this is how the values have been computed at each of these steps. And the last class we said this value could be expanded in an interesting way, which is you look at all the possible next states that you could transition to, right? So S prime, summation over S prime of reward that you have for going from S using some action A, where A is coming as per the policy, to S, let's call ST, A S prime into probability of plus something okay, you directly jump to the value part, but what was the, let's write it kind of by brute force, right? What would that be? Just enumerate all the terms. So some plus gamma, but what about probability here? I mean, I need a probability here also, right? Something else? So this R should have been in the bracket, I believe, yeah. R should have gone into the bracket. Plus another summation S double prime blah blah blah, right? So the same thing is now going to continue. A prime from policy times probability of transitioning to S double prime given S prime comma A prime and so on. So this is the structure that we found repeating. Good point. So the question was about stochastic policy. Let's just complete this. So this, what did we say? If this entire thing could itself be viewed as the value function at S prime, right? So the question was, what if pi was stochastic? This value function is under deterministic policy, but suppose we had a stochastic policy like this. All you will do is slap on the probability somewhere, but while slapping on the probability, will you have one more summation across all actions? This is assuming one's action, right? So suppose you had stochastic policy. For stochastic, what would you do? This, instead of just A from pi, what would you do? You would have one more summation over all possible actions, north, south, east, west, all the actions into the probability of pi of A given S P into everything else. Likewise here also you will have a summation over A prime action into the pi of A prime given S prime and so on. Does that answer the question? So you will have few more summations.
Probability of S prime given is combined by some summation of this multiplied by
yeah, so you are basically replacing this probability with this probability multiplied by right weight, but I mean this, it is a weighted sum, so probability has to be multiplied with this pi. If you just take this summation pi here, then it will just be 1, right? So that's why I said you have to insert this entire thing here. But in any case, whether it is probabilistic or stochastic, do you find that the structure is repeating itself? V pi st and V pi s prime, the same structure, whether it is probabilistic or stochastic. Is that fine? Okay, and that's what we leveraged in the last class. We didn't of course discuss the probabilistic part, but For the fixed deterministic part, we did discuss, and we find this interesting. This is just a recap from this particular slide. So we find that this entire substructure is being repeated, but for a different state. So in both cases you will find this interesting Bellman equation, stochastic and deterministic pi. You could also make use of the fact that the return GT, the cumulative reward itself could have been returned recursively. That's another way you can write it, right? GT is RT plus 1 plus gamma times GT plus 1, the cumulative reward. Right? This entire thing is what we were referring to as GT. But now you can write GT as RT plus 1, separate this out, into gamma times GT plus 1. So even if you use this fact, you should be able to get this Bellman's equation. And one important point here, now I suddenly started talking about neural networks here, if you noticed. And what we are highlighting is that the policy pi, which is something you could also approximate using some neural network. Okay, so it comes to learning, we are not going to get into details here, but there are these placeholders. How do you get the policy pi? Instead of searching over a space of all possible policies, which is all possible paths through the maze, making it a combinatorial search space, you can say, well, pi is going to be a neural network, which I want to maximize over all the model parameters of the neural network such that my value function is maximized. Okay, so this was the Bellman's equation, and in fact even the value function could be approximated using a neural network. Again, this is again small placeholders for you to think about. Yeah, this is food for thought. These two are examples of food for thought. How could you replace the policy pi could be approximated, so can the value function. In fact, in the last class I had also talked about a Q function. What was Q function? Q pi. What was the difference between Q and V? Yeah, so value function was the expected cumulative reward with possible discount. Q function is at the current state S, if I took an action A, then what is the expected cumulative reward? That's the only difference. So this question was, policy is time independent. How do you make policy time dependent? Policy is time independent, but it is state dependent. So that's actually what matters, because if I land up revisiting the same state, I want to be able to learn from, I want to be able to plan in such a way that my previous experience counts. So it's state dependent, not time. Mm-hmm.
Initially, you want to policy which allows you to explore the space as much as you can, and after you have sufficiently explored, you want a new policy which takes the optimal path.
So you are talking about learning the policy. Yeah. So let's that's I said, that's food for thought. I don't want to. So. The modeling the policy, estimating the parameters of the policy can be done using neural network, but the problem we are now still talking about is how, given some value function, given some reward function, how do I find the best policy? We are still talking about a planning problem. See, this is finding the best policy is a planning problem. And what is a planning problem here? you want, given a fixed maze, the agent needs to plan how to reach the goal. That's planning, right? Now I might have a combinatorial number of possible step sequences through my policy, right? Or I might approximate the policy using a neural network. That's really the method I am using, but it's still a planning problem. In both cases we are talking about planning. Whereas when I model the value function itself using a neural network as mentioned here, we are actually talking about learning parameters of the neural network so that the value function is meaningful, representative. That's a learning problem. Okay. So imagine I give you lots such mazes. So every time I try and reach the goal, I am now associating value. What is the right value? What is the right reward? We are very dumb. We said -1 reward everywhere, right? Is that the right thing to do? Maybe I should have had a different reward. So how do I carry forward my learnings from one maze to another maze? That's a learning problem. Given a maze, how to find the path is a planning problem. Is that clear? I'll just write this again. Okay, so planning is given a maze, fixed maze, how to navigate, right? How to get to the goal, finding best pi. Given a maze and given a value function. So when I say given a maze, I also mean given the value function and all that, right? Okay, so when you associate, for example, a neural network for the value function in equation 5, we are concerning ourselves with the learning problem. Yeah, so when you say V, then this reward is part of it. I mean, yes. So again, let's not get into the details. So you'll structure it in the neural network in such a way. So in fact, often you don't even do V, you actually look at Q. So Q learning. Right? So you could instead of learning V, you can be learning Q. So yes, you are right. Because this Q is more specific. If I took action A at step S, what would be the expected cumulative reward? Okay, so again, you have this Q learning associated with learning Q. Whereas in the previous slide, when I talked of approximating the policy, we are still talking about planning. Think of this as addressing the planning problem. Yes, any question? So his question is how do we make the state structure independent of the maze so that learnings can go from one maze to another maze. So that's again a design problem. How do you, I mean, for example, the state could just be me and my neighbors, for example, instead of getting the absolute position. So when I say agent's location could be very relative location. How do my 4 neighbors look like? Am I facing the wall? Okay, and the optimal policy, finding the optimal policy is basically finding that which maximizes my value function, right? That's the planning problem again. So, and there again the Bellman equation comes to our rescue. Right, this is the Bellman equation here, the structure that we wanted, and this is again this maximizing problem, maximizing over A or all policies. It's a planning problem. Though the Bellman equation can be used for learning as well, right? V pi s, the one equation 5 is also Bellman's equation. The Bellman equation holds for V pi s and also holds for the optimal plan. That plan, that pi which maximizes the V pi. Okay, so just note this difference. Here you are just expected value, whereas here you are talking about max over A of the expected value. In both cases the Bellman equation holds. So if you just let's say I apply a max here, expected value here, so max here, right, max summation. Now for the time being let's forget this probabilistic transitions. Now this max, if I want a max of the summation, right, max of the summation, how is it relationship, what's its relationship with the summation of the max? So I put a max here, instead I find the max A and the max here as well, right, the next transition. So what's the relationship? Upper bound, lower bound, exactly the same. Sorry? Max of the summation would be smaller than the summation of the individuals, but we can show that in this case it will be exactly the same. We are not getting into mathematical details here. Understanding the problem itself I think is going to be challenging for some of us. Okay, and this is the optimal policy, obtaining the optimal policy using the value iteration algorithm. We discussed in the last class, also in the lab, but this is basically the whole algorithm summarized. So all you are doing at every step is updating your estimate of V, the teeth estimate of V pi, actually V star, which is looking at the V with the best possible policy. So you estimate this from a previous estimate of V, but the previous estimate of V is at all states S prime from where to which you could transition from S. Okay. So here you have the t plus 1th estimate and you go from S to S prime using action A, and across all such S primes you take the previous iteration t, the previous iterate of Vt and compute the V star t plus 1. This is basically the process. And you keep doing this till the V star estimates from the t and t plus 1 iteration are very similar. Well, basically convergence criterion. Once you get your V star, you could get your pi star. So pi star would just correspond to that action which maximizes the current kind of expected reward from the transition from S to S prime plus whatever else came from the optimal value iteration algorithm, right. So this part you are going to try and see which A maximized this component plus whatever came from all other best possible choices of actions. Okay, so that is the estimate of the optimal policy. Okay, so this same structure is here. All you are now interested is finding the A that maximizes the transition into an S prime such that following at S, starting at S prime, we have best possible policy corresponding to the V star already determined. So what's the time complexity of this algorithm? And also other alternative algorithms. Could we think of alternatives to solving this? All for solving this. What is the time complexity? At every iteration, what are we doing? Across how many states? Across all the S states, right? We need to iterate over all the S states. This. So as far as time complexity is concerned, note that this is for all S prime in S. And again here also, you need to compute the V star also for all S in the set of states S. And what else? You need to consider all the actions here for all A in capital A. Which one? This one? This state? This one? Which step are you talking? This one? Why V star minus? Okay. So basically, what we want at convergence is that V pi st is exactly obtained using this equation from all other V pi S prime, right? All we did in this iterative algorithm is we put a superscript t and trying to get the t plus 1th iterate from the t. At convergence, what would you like? The fixed point, right? What would you like? The t plus 1th iterate is exactly agreeing with the t plus 1th iterate itself. That's what the convergence criterion is, right? So I mean this should become independent of t. And the way we can ensure that the independence of t is that they exactly coincide. But instead of looking at exact coincidence, which again if you look at tutorial 9 problem 3, we do give some bound guarantees. So we are saying that, well, at convergence I will not be able to guarantee that it will be exactly the same, but it will be really close enough. The iterates would converge to become very, very close across iterations. Is that fine? So you are saying that V star t is almost equal to V star t minus 1 or t plus 1 or whatever. That is the requirement. Is that fine? So what about time complexity? We are discussing time complexity. So we need to compute this for all S, V star t plus 1 for all S, in terms of V star t for all S, and finding a max across all the actions. Okay, so this is for all S, this is for all S, and across all the actions. So what would that be? Size of S into size of A into again size of S. This size, okay, so again this is the first size, then the size of A is coming from here and this size of S is coming from here. So you look at all states, you are basically looking at interaction for every pair of states and through every possible action. That's in simple plain English, that's all you are doing. And therefore the complexity, computational efficiency will matter here because we are talking about planning, right? So this is planning, finding best pi, which is to reach goal in a maze, right? So obviously you need to be fast and efficient, and what this does is it looks at all S prime and all A, okay. This is looking at all possible combinations of the 3, and therefore it will be order L's k square, where k is the number of states, L is the number of actions. And if you do this for n iterations, this is the complexity of one iteration. If you do this for n iterations, you will have n times this L into k square. So basically you are saying n into size of action into size of state square. The max operation on the other hand just requires you to scan this whole thing once. The max operation here. So for the max you will have to find for a given state. I start from let's say the start state in a maze. I look at all the possible actions and all possible states. That's it. So I don't have to enumerate for all possible combinations of states. So I might just start from the start state and find, there's my start state. I already found the V star, right? I'm going to use my computed V star and all possible actions I could have taken from here. For every action I would look at the V star at the landing state and then decide which action I should have taken. Then I move to the next state, and then from there again in turn it will explore all the possible actions that lead to transitions. On to the transition state, what is the V star? So it's just one scan. I don't have to look at all possible state cross state interactions. That's already done. Okay. So this you don't have to. This is to begin with is the start, and then the scan between these. So it will be order of A, size of action into size of states. That's it. That's what we have here. Size of K into size of L. Now could you think of alternatives? What else could you have done? So here are some possibilities. So somebody may say, well, all this just basically looks like some maximization linear program with a maximization, right? So you could solve this as a linear optimization program where your variables objective is over variables which are these V's, and you are considering a linear combinations of the V's. These are just a linear combinations. In fact, when I asked for suggestions in the last class, some of you said, oh, why not take non-linear combinations? So you did identify this as just a linear combination. So you could solve it as a linear optimization program. Linear optimization, by the way, there are no guaranteed polynomial time algorithms for linear optimization. And then policy iteration is another way. Instead of doing value iteration, what you could do is iterate on policies. Fixed start, it's like gradient descent. Think of starting with the policy and then choose let's say this is by pi. I fix this policy pi. I then now try and just solve this linear system. Forget about maximization. There's no maximization, just linear system for a fixed pi. Solve this linear equation. So it's not a linear optimization program, it's just a linear system. It's like Ax equals B. Solve that, and now based on that decide how to refine my pi. I had a particular policy which was always take left. Let's say my starting policy pi is always go north. I mean, stupid policy, but let's say I do that. I start with that and then I find, well, what is the V pi for this stupid policy of going north always? I'll find some V pi, and then based on that V pi I refine my policy. I say, maybe one of the few of these positions I could have gone to the right because the V pi there was probably very low. I decide to slightly change, I mean you could try this heuristically, changing the policies, refining the policy slightly. So choose a policy, solve S linear equations in S unknowns, where the S unknowns are again the V pi's, the same unknowns in both linear optimization and policy iteration, and then improve the policy at each state S. So this policy iteration a bit more complex, often it's slower than value iteration, so therefore we are not going to the details of this, but this is a basic idea. So in both these options that we discussed, we are talking of the V's as the unknowns. That's the key point. All these are the unknowns. Okay, so I talked about the learning problem earlier. I'm just there's a couple of slides which I plan to skip. But the model has this problem of predicting what the environment will do next. What is the reward that I should be using? Somebody pointed out that what we should be learning reward as we move from one maze to another maze. So I mean these are aspects of the learning problem. State model S predicts the next state and reward model R predicts the immediate reward. These are the two components we are trying to learn. So given S, A set of actions, gamma the discount factor and the facility to follow a trajectory by sampling from probability distribution and reward distribution, how can we find an optimal policy? So this here you need to sample from the possible P's and the R's, right? The P's and the R's. You need to sample from them efficiently, you need to search that space efficiently. So this is learning a model, this is learning problem. Okay, so I tried and summarized everything that is we were talking about on the board itself. So sometimes you as I said you could use neural networks to approximate the pi's in the planning setting, and in learning setting you could use a neural network to approximate the Q. So Q learning, again your objects could be complex, could be images, you could do convolution and so on. Again I am deferring this discussion possible in last class, but then there are lots of agents. So for example you could have only value based agents with an implicit set of policies, but you need a value function. You could have policy based agents, no value function but only policy. You could have actor critic where you have policy and value function. So and so on. So each of this can probably take a class of its own. Okay. So and then you could also have cases where you are also trying to model the unobserved unknown situation of the environment. So for example the observation may no longer be Markov because you have not observed everything in the environment. So that takes you to the space of partially observable Markov decision process. Again as I said this is optional and deferred. I gave this example in the last class. So you can have two states of the agent is in two states with respect to the environment, but the two states are not distinguishable, right? They look so similar. I mean locally they look so similar. I might try and model the environment using not what I have observed but using some hidden states. So that is why we talk about partial observation. I am going to now spend a few minutes just talking about one more interesting shootout of the discussion we had on graphical models and recurrent neural networks. I felt that for better appreciation of recurrent neural networks you should understand what graphical models are and specifically what hidden Markov model was. So recap in the last class, at the beginning I said, well, you take a hidden Markov model, one way you could think of extending using Markov decision process is when you associate actions with state transitions, and that is how we have got into this discussion, right. The other view is the one on the right. Okay, so imagine that you allowed instead of one of n states in a part of speech tagging example of hidden Markov model, instead of one of n part of speech tags, suppose you had a distributed hidden state which allowed storage of more information. Okay. And an example close to home is your autocomplete in WhatsApp or any other chatbot. So let's say you are also fascinated with machine learning, that the only example you could think of is MACH, and you expect your WhatsApp is smart enough to have figured out I, right? Because you think WhatsApp, that's all it does, machine learning. Okay, so now I want to be able to model this behavior. Given MACH, IN is what it should come, and E and so on, right? How do I make this happen? So when there is M, I expect an A. When there is A, after A I would have expected a C, H, I, and therefore N and E. So this is a more complete behavior, right? And now what we are saying is the bridge between these two is through some hidden states, but instead of now kind of discretizing the hidden state to be one of n, oh either it's noun or verb or whatever, I say well it could be multi-valued, distributed, so that you can store more information just beyond part of speech tag. So that this could be domain, it could, instead of machine, it could have been macho or Mako, or I don't know how you pronounce it. If you are watching lots of Hollywood, you want a different kind of auto completion to happen. So each of these hidden state depends on maybe the domain that you are talking about. Perhaps it's not English at all, right? We are too biased towards English. Maybe it should have been some other language, say Portuguese, which shares a large character set with English. So the hidden states could mean multiple things. So this could be domain, this could be language, and now we also have, what do you call them? These emojis, right? Emojis. So why? I mean, after n, in place of n, I would probably want some machine learning model emoji to come up. Is there a ML emoji so far on WhatsApp? No, not as of now, right? But let's say, how do you spell this? EMO or IMO? Okay, I have not used them. So emoji, is this the right spelling? Okay. Okay, so these are hidden states. So I'm trying to motivate, why would you be interested in storage of more information, a distributed hidden state, right? And this is exactly, now you see the values here, and the values here could be domain, maybe the first one represents domain, the second one could represent emoji, and the third one could represent language. And now you see some values associated, 0.2, 0.6, 0.2 at every step. So I mean, in the case of convolutional neural networks, you recall we did parameter tying, we shared parameters. What parameters did we share in CNN? With what in mind? Spatial time. So in CNN you had a spatial time, the car whether it occurs here or somewhere else should be the same. What else? So that was kind of location invariance, but spatial also is that I only look at my neighborhood, right? To find that this is the tire of a car, I don't need the entire car, I just need a local neighborhood, and I believe that successively at higher levels of granularity I would be able to assemble the car, but while doing the tire I need to get the neighborhood of the tire well, and that's how jigsaw puzzles are also made, right? You look at your immediate neighborhood and gradually get the bigger picture. So we use the trick of common parameters, locality, so we had this equivariance and so on, right? And then we had also pooling, downsampling and so on. So in RNN, the recurrent neural network, our intuition is that we want parameter sharing in the following way. We want first a neuron's output at time t to depend on its time in its state s at time t minus 1. So we have the notion of state coming from hidden Markov models, and we also now talked about state so much, Markov decision processes. Okay, so the state at a current time instance should depend on the state at the previous time instance, and the same thing here. So there is this edge going between these. Okay, you can think of this as like you would have in your fully connected network. Okay, so this is one aspect. There is no parameter sharing immediately we talked about, but then yes, we are talking about state at time t determining the state at time t plus 1, but each of this is a vector now. This is a vector that we are talking about. As I said, multi-valued instead of just one of k. And in this context, the question would be, would you want this network to look as the same as this network? Yes or no? So if I am typing a word in Portuguese, most likely I continue typing it in Portuguese. It's very unlikely that I start 3 characters in Portuguese and fourth one I suddenly think let me write it in English. It's very difficult to write. I mean, I don't think languages are so flexible and malleable that you can keep switching between languages within a word. Across words you may, right? So the idea is that if I have a particular state transition happening from st to st plus 1, I mean the parameters for the state transition from st plus 1 to st plus 2 should be shared, and that's somewhat intuitive, and that's what RNNs do. So RNNs say that this network, these weights, they are shared. They are the same parameters across time instances. So here we call them Wt minus 1. So I don't know if you are able to see this properly, but this is Wt minus 1 and this is Wt. But in the parameter sharing, the intuition 2, with that, the W's all, this all becomes W. I mean a weight vector, but the same W across time steps. So that's the recurrent nature here of the task. What are we doing? We are basically performing the same task for every element of sequence, the same hidden state behavior, not the same hidden state. Hidden states can keep changing, as we will see in the next example also. So the hidden states can keep changing. I mean hidden layer 0.1, minus 0.4, 0.3, 0.6, 0.2, minus 0.5. The values of the hidden state can change, but the underlying mechanism that governs the change remains the same. Okay, that's the idea. And the goal is that you are able to go from an initial state, MACH, ACHI. So initial state of the network, you will find that, oh, initially A had not the highest probability. In fact, the highest probability was somewhere else. 0.5 is for some other character. But then you want to get to the desired state. But I will just explain this in a few, one more point. So there are two views of the neural, of the recurrent neural network. What I have shown on the board here is the unfolded state, right? Where unfolded state, I don't show the parameter sharing explicitly. This is the unfolded state. But if I had to show a folded state, what would I do? So folded state would just be one like this, something like this, where you see a character as input and you want another character as output. This is the folded state. Yeah, but in a vector sense. So his point was, sorry, couldn't hear him. He said st is w times st minus 1, but I said yes, times in a vector sense, yes. So the question is, what is OT and what is X, right? So that's exactly where I am coming to next. So this is X, for example, this is X t minus 1 xt plus 1 is ot minus 1 ot plus 1 and so on. And when we represent this here, we are just referring to this as x, the input as x in the folded case and the output as O. So his question I think is, what about the representation of x and O? Are they just single bits? What do they correspond to? Right? So the question is, should O be V times St or W times St? So first of all, let's get into the representation of O, what O and X look like. So a very standard practice is to use this so called one hot representation for words, for characters, and RNNs are very much driven by natural language, right. So we will talk about words and characters here. So the one hot representation says that, well, if I had 3 characters A, B and C, only 3 characters in vocabulary, then all I need to do is have a 3-bit vector where exactly one of them is turned on, the others are turned off. The one that is turned on corresponds to the index for that character. Okay, so the indices are basically for A this is 1, this is for B and this is for C. Okay, so with this representation, now let us understand what the math would be like. Okay, so we want from initial state of the network to get to a desired state. So initial state, let us say we have considered some 8 characters here, right, 8-bit representation assuming just 8 characters. This is again as an assumption. If you have right, if you say have 100 characters including math symbol and other basically Unicode, say you will have 100-bit vector. Here we have 8-bit, and initially we would have liked this to have peaked, sorry this A to have peaked here. So this is the index for A, but unfortunately it is not peaked, it is just 0.3. In fact, something else has peaked, 0.5 has peaked, which means after M the network initially is not suggesting A, it is suggesting something, some other character. It is not yet fond of machine learning, right. So how do you make it fond of machine learning? That is the target state. So the target desired network state after training. Now what are the other parameters governing this interaction? Okay, so we said we have these weights between the hidden states, we call them WHH. We also have weights between the input character represented in one hot and the hidden represented in, again it's a multi-valued vector, right. So what would this WXH look like? You have X, you have H, this could be fully connected. So every bit here can interact with every bit here. Likewise for the output also I could have one hot representation and I could have a fully connected network. That is a possibility. The interesting thing is parameter sharing here. This is WHH, this is WXH and this is WHO. Okay, so I am going to avoid more math here because a lot of this is basically based on just the neural network architecture, backpropagation that we have learned. So you could do backpropagation here. To get to the desired state from the initial state, you will do backpropagation. You will do backpropagation so that the next character will be what you have in the ground truth based on the current character, and the hidden state the weight should have all get adjusted. The only math trick here is the back propagation through WHH, because these are routine, right? WHO and WHX are very routine. WHH is the tricky part. So you need to do some back propagation through time, because when this WHH is unfolded, it looks like this, right? So when you now do a back propagation from the next character sequence to the current character, you will need to ensure that these weights are shared. These are not different weights. So it's the same question, right? So question is, in the folded case, in the folded representation, when you do a back propagation from O to H to X via H. So W is basically all these cross connections, right? So I showed this. So it's easier to see in the unfolded case. So every state connects to every. So in the folded state, will the at every time, every epoch, will the values get updated or will they remain the same? So there is a bit of accumulation you have to do across time. So that's exactly the trick. The trick is back propagation through time, which I will not be able to discuss. If I get a spare class in the end, I will try and do that. Okay. So this is a trick. The trick here is in back propagation here.